All right, so let's take a look at the warm-up here. We have a big warm-up today. A little bit of a reminder of some of the last few sections as we kind of start prepping for midterm 2. So we're given some function. There is our function, 1 over x plus 1 quantity squared. We want to plot this thing. We want to find the area under this curve to the right of the y-axis. After that, we're going to consider a little truncated region of this underneath this function. Find the perimeter, find the volume of rotation, and find the mass. So it's really a whole bunch of stuff with one function. So let's go right through them here. We'll start with the first one, the plotting the function. Of course, you can throw this in your calculator and plot it, but some of these you want to be able to maybe sketch the plot by hand. So the way you might approach this, if I want to just sketch out a plot real quick, is say, okay, I might have a sense of what 1 over x squared looks like. 1 over x squared looks something like this. Right, in that first quadrant anyway, it also looks like that. Now 1 over x plus 1 quantity squared is just doing a little shift, right? It's changing the argument of my function. If this is f of x, if f of x was 1 over x squared, then f of x plus 1 would be 1 over x plus 1 squared. So we're just changing the argument of a function, you could say. And so what kind of transformation is that? Shift, absolutely. It's a shift to the left. Come on. There we go. All right, so really we're just shifting our function to the left by 1. Our function is going to look something like that. Any questions about the plot? What's the height right here? 1. Plug in x equals 0, we get a height of 1. So the next question is find the area under the curve to the right of the y-axis. That would be all of this area. From x equals 0 to where? Going to infinity. So if I wrote out this integral, it would look like the integral from 0 to infinity of 1 over x plus 1 quantity squared dx. That would be the area under the curve. Of course, if we look at this as an improper integral, can we find this area or can we not find this area? We have to go through the improper integral process. So I'm going to rewrite this as the limit as a goes to infinity of the integral from 0 to a, 1 over x plus 1 quantity squared dx, like that. I'm going to keep my limit notation. I'm going to do that integral. Looks like I should get x plus 1 to the negative 1, the negative sign in front. That's kind of like a guess and check approach. If I took the derivative of that, my negative 1 would come down. I get x plus 1 to the negative 2. That's what I have. So that worked out well. If I'm a little worried about that, I can do the more formal substitution. I could let w equals x plus 1 and go through that process. This is from 0 to a. Give myself a little more room here. So then I have the limit as a goes to infinity of negative. Then I have 1 over a plus 1 minus 1 over 0 plus 1. All that stuff. And then I evaluate my limit. As a goes to infinity, what happens to the first term here? It goes to 0. This one goes to 0. As a goes to infinity, what happens to my second term? It just equals what it's equal to, right? There is no a in that term, so that one is just equal to 1. I have a negative and a negative, so that turns into positive 1. So the area under this curve from x equals 0 out to infinity is just the number 1. Any questions about that one? Remember that work is important. You will get marked off on the exam if you don't write the limit as a goes to infinity of this stuff. If you don't rewrite it as the limit of a proper integral. That's what we're checking for. All right, then we go to the next one. So let's see. Now we're considering a region. So if we go back up here, maybe I grab my plot, drag it down a little closer to where we're working with. Now I'm not going out to infinity. Now I'm just stopping at x equals 1. I'm really just looking at this region in here. to find the perimeter of that region. So now we have our region, something like this. I need to find the perimeter. Well, the perimeter is just the sum of the lengths of the sides. So let's look at some of the different sides. What's the length of this side? 1. Right, we know when x equals 0, we have a height of 1, so that's that value. What's this value right here? Now it's also just 1. We're going from x equals 0 to x equals 1. What about this side right there? What is that one? And how did you get that? Absolutely. Plug in x equals 1 into our function. We have 1 over x plus 1 squared. So this looks like 1 over 2 squared, or 1/4. I have 1/4 there. So far we have 2 1/4. Now, of course, the tricky part is finding this length right here. Well, this length is just the arc length. So once again, we'll give ourselves a little more room here. When we calculate our arc length, we're going to have a value for the derivative of our function. So if our function was x plus 1 to the negative 2 power, then our derivative is going to be negative 2 times x plus 1 to the negative 3 power. So that's our derivative value. So the arc length, this side over here, is going to be the integral from x equals 0 to x equals 1 of the square root of 1 plus my derivative value, x plus 1 to the negative 3, quantity squared dx. So it's the derivative squared. 1 plus the derivative squared. So all that stuff plus 2 1/4. And this all together will be my perimeter. Questions about that one? All right, and then the next one, the volume of the region rotated about the x-axis. So once again, we have our shape here, and rotating about the x-axis. So it's going to look like this piece over here. And if I draw my cross sections, one slice of this volume will look like this. It's a rotation, so the cross section is circular here. So in this case, my cross section is going to be a disk. So I just want to find one slice of the volume. Here is my delta V. It is a disk, so it's going to be pi r squared times some thickness. What's my thickness here? Delta x. Now all I got to find out is what is r in terms of x, and what is my radius value here? The distance of the function. This is my radius if I draw it on here, and that is just the distance from the axis to the function. So it looks like my volume slice is pi times x plus 1 raised to the negative 2 power, all squared, delta x. That's my pi r squared. And the total volume would be the integral from 0 to 1 of all that stuff. Yep. Yep. Any questions about this one? All right, and then we have a last one here. Same region. But now I'm given a density. So now my region is a thin metal plate with a density equal to 3 kilograms per square meter. It says find the mass of the region. So I might not be able to do it all at once. So what I'll do is I'll cut a slice. That would be a good slice. So let's just find the mass in that slice. Well, if I want to find the mass, which is maybe kilograms in this case, I need to take my density and multiply it by something meters squared. I need to multiply it by some piece of area. So really, this mass problem is just an area problem. And this area is just the height of the side here, which is the function value, x plus 1 all raised to the negative 2, times the thickness delta x. So that gives me an expression for just the mass in the slice. And the total mass is just adding all those pieces up from 0 to 1. Any questions about that one? All right, any questions from the homework, or from the warm-up? Yep. All right. Let's look at 8.4. It says find a Riemann sum that approximates the total mass of a 3x5 rectangular sheet, and then part B says calculate the mass. Does that sound right? Okay. So in the book we have a Riemann sum which approximates the total mass of a 3x5 rectangular sheet. So we have a 3x5 rectangular sheet, and one question is it 3x5 or is it like this? In which case are we dealing with here? We're going to tell us that the density per unit area at a distance x from one side of the length 5 is 1 over 1 plus x to the 4th. I'm sorry, 1 plus x to the 4 in here, like that. And this is mass per unit area. They don't tell us the details, kilograms per meter squared, or whatever they want it to be here. But this x is measuring the distance from the side of length 5. Right, so if we think of x as a horizontal distance, which picture am I talking about? The first one or the second one? And this one's the second one. So if I'm measuring x, like I said, horizontally like this, then it's the distance from the side of length 5. So it would be this case. All right, so now I have my picture that I need to work with. And it says find the Riemann sum which approximates the total mass, and then the second part says calculate the actual mass. So I'll kind of do them together here. So in general, I can't find the mass by taking the density times the total area, because my density changes. My density is a function of x. So instead, I can cut a thin slice. I cut a slice because as long as that slice is thin enough with respect to x, then my density doesn't change inside of that slice. That means inside of my slice, the mass is just the density times the area. That's not true in general, but as long as my x doesn't change very much, it's true in my slice. So if I write out this expression here, my density was 1 over 1 plus x to the 4th. And then I should need my delta A piece, which would be the height times the thickness. The height is just 5 in this case, and the thickness is delta x. So this would be the Riemann sum that they're looking for in part A. And then to find the total mass in part B, it's just adding up all those slices, taking the sum, taking the limit, in other words, taking the integral. So if I integrate this thing, 5 over 1 plus x to the 4th dx, from 0 to 3, that should give me the mass value. Any questions about that one? Well, that integral doesn't actually look like a whole lot of fun to me. So I think the focus on this section is probably setting these integrals up. So you should do that one in Mathematica or on your calculator or something. That's a good approach in this chapter as well, that if you get stuck, you're not sure how to do the integration, it's good to try them by hand, but if you get stuck, put it into something like that and look at the answer. And if the answer is a hyperbolic elliptical arctangent, they don't expect you to do that by hand, right? So, all right, other questions? All right, let's finish up our lesson for 8.5 here. All right, so last time we were talking about kind of the introduction to these new physics problems, work, and later we're talking about force and pressure. And so we set up the formula they gave us in the book, work equals force times distance. We talked about why we need to use integration here because that force is no longer a constant. Like it was, we talked about the definition for work as vectors. So we kind of talked our way through this first chain problem. How much work does it take just to make this chain move just a little bit? And because the weight of the chain was changing as we pulled it up, we need to set up an integral. So we kind of finished that first problem, and we're really starting to work on the second one, the work to empty a tank. And the idea was this one didn't match our formula so well. So I wanted to set it up, not so much that this is a different formula, but this is how we might think of this process for dealing with this type of problems, emptying a tank problems. So the idea is I need to find out a little slice of work. I have to do an integration on this one because I can't just take all the volume, however much it weighs, and move it some little distance. Or move it some fixed distance. Because if I took all of the weight inside of here and I moved it 3 feet, what would the problem be? So I'm trying to find out how much work it takes to empty the tank. It's full of water. I got to pump all this water out. And so I got to figure out how much work it takes to pump it out. What's that? Absolutely. So if I take all of that water and I move it a distance of 3 feet, that means I'm taking this water right here and going, all right. And so I'm not pumping it out of the tank. I'm pumping it for some reason to a height of 2 feet above the tank and then getting rid of it. Okay, so that's why I have to use integration. That's not why I can't just say, here's how much weight this thing is, how much force I need to move it, in other words. I can't just move it 3 feet. So to kind of fix that problem, I'm going to look at a thin slice. I'm going to look at a thin slice of the volume and just find out how much work it takes to move this slice of water out of here. It's always the same setup. Big problem, I don't know how to do it. Let's look at a small little piece of the problem. Okay. Now once again, force times distance, well, the force I have to apply to this little thin slice is exactly opposite to its weight. I want to move it, I got to battle against the force of gravity here. So I'm just calculating its weight in this slice. Okay. So basically I want to find out the work it takes just to move this slice of volume out. That means I'm going to take some weight of this slice and move it some distance. Okay. So if I'm measuring some distance h up to my slice there, how far am I moving this slice? Absolutely. So 3 minus h is the distance I'm moving it here. So it's kind of going to be like distance times force here. Distance times force. And the force, once again, is the weight. So now how do I find the weight of the water in this slice? What is it? Volume times density. My density is kind of telling me how to do it, right? My density is pounds per cubic foot. Well, I want the weight. I want pounds. I got to take this density times the volume. So density times just the volume of my slice, which is very thin, is going to be equal to the force I need to move this thing. So there it is. That's the work it takes to move this little slice out. Now I want to find the total work to empty the tank. I add up all my slices. So really, this work problem is just a volume problem in disguise. It's a volume problem with a couple coefficients out front. So now I can finish it up here. Now I have a couple more steps that are challenging from the volume perspective. I have my 3 minus h. I have my 62.4 pounds per cubic foot. Now what is delta V? Well, it's going to be this distance, the width, times the length times the thickness, which in this case is delta H. What's my length? That one's just 15. And then what's W? Well, to find W, I got to set up my similar triangles. So I have a big triangle with a base of 2 and a height of 3. And then I have a little triangle where W is my width and H is my height. So using my similar triangles, I say W is to 2 as H is to 3. So that tells me the relationship between the width and the height here is W is equal to 2/3 H. So my delta V is really 2/3 H times 15 times delta H. And then my total work is just adding all those things up. From where to where? Zero to 3. And it kind of looks ugly when I just throw it all into my integral like that. But really, I have 62.4 as a constant, 2/3 is a constant, 15 is a constant. I can multiply all those together and just pull it right outside of my integral. And so I'm really just integrating 3 minus h times h, which is just going to be a quadratic. It's just going to be a polynomial, which is pretty straightforward to integrate. All right, questions about this one? It's really just that process. How much work does it take just to move one little slice of the volume out of here? So we're just finding the weight in that slice and multiplying it by the distance. It's really just a volume problem. All right. Last thing I want to cover before we get into a bunch of practice problems from the homework is this idea of force and pressure. The last topic in 8.5. All right, so there's some big ideas that we get kind of from physics here, these equations that we're going to need to use to solve these problems. So the first one is our formula. Pressure equals force divided by area. It's a formula. Like, oh, we got to memorize another formula. Now, the way I remember this formula is because I have to fill up my car tires with air in the winter, right? And so I know how much air I want to put in there. I want to get to a certain amount of pressure. I put whatever pounds per square inch in there. And so when I look at that, I say, oh, pounds per square inch, that's the unit of pressure. Pounds is a measure of force. And square inches is a measure of area. Right? So if that's something you've done a lot of times, right? Come the beginning of winter, fill up your tires with air. Is that the way it works, or is it the other way? When do they run low? Is it the beginning of winter or the beginning of spring? Okay. Here we go. Okay. So if you're used to doing that and you're used to your units of measure, those units can really remind you of the formula. Pounds per square inch, force per area. Okay. So that's the first thing. We have to have our formula all set. Now, it turns out we're not even going to use in that form very often. Usually we're going to multiply through by A to get force equals pressure times area, but it doesn't really matter, right? We're just multiplying through A to get that other formula as well. The next one is that pressure is the same in all directions. It exerts this force in all directions. So if this is my little box, there's a certain amount of pressure that goes like this, and a certain amount of pressure that goes like this, and like this, in all directions. And this is a really important, powerful piece here. Because what we're going to do in this section is we're going to take objects full of fluids and find the force on the face of these objects. So we'll have something like a dam here. We'll say, what's the force on the front of this dam? And it's really good that pressure exerts the same amount of force in all directions, because if it didn't, we would have to build incredibly strong dams. Because this river back here keeps going for miles and miles and miles, and if all that water was really pushing against our dams would never stand. But the fact is, there's a certain cube of water right here, right next to the dam, and it's exerting some pressure on the dam, but it's also exerting some pressure on the cube of water behind it. It exerts this force in all directions. So it's not a cumulative effect of all this water pushing on this dam, because that pressure at depth is pushing in all directions, even backwards. Okay. Any questions about that concept there? Okay, we're going to remind ourselves about that one later when we actually work some problems here. So that's the first one. And then the last one here, we have a little formula. Pressure equals density times G times H. It's a formula to calculate the pressure. So if we have some box of water, and we want to find the pressure at different spots in this tank here, we have a density, and this is, as it's written, this is a mass density. This is a mass density. And then we have that times G. G here is the force of gravity. It's that gravitational constant. Okay? So we think about this. We're going to have a density like 20 kilograms per cubic meter. That would be an example of a density. We're going to take this thing and multiply it by the gravitational constant. And then we're going to take this thing and multiply it by some height, maybe measured in meters. And this thing should all work out to be a force divided by an area. And it does, because we have kilograms times our gravitational constant. That's a mass times gravity, and that gives you a force. So those two combined give us a force. And as we cancel out one of our units of meters here, we'll be left with meters squared in the denominator, which is a measure of area, of course. So we do get our force divided by area. Okay, any questions about that piece? Now I'm stressing this, units, because this is our formula for pressure. There it is. But that formula assumes that we're having a mass density. So if we have water in our tank instead, and we're told that the density is 62.4 pounds per cubic foot, how does that change my formula? I don't need G, right? Because this is a weight density, and that weight is a force. When they say pounds, they're giving me a measure of force. I don't have to adjust my mass and multiply by the gravitational constant to turn it into a force. So we're going to use this formula. But you need to understand that if you're given this density, that's a weight density, that combines both of these terms right here. And you don't have to take this thing and multiply it by G. Okay. All right, so those are my 3 big points here that we're going to recall as we start off our discussion about force and pressure. Any questions about these? All right, now let's look at a problem. Okay, some of this will be a little repetitive of the stuff that's in the video, but there's usually lots of questions in this section, so we're just kind of going to go over these base problems again. So we had this tank. It's a fish tank. It's a tank of lobsters in a restaurant. All kinds of ways to do this, right? Filled with water. And we want to find the force on each side and on the bottom of the tank. So we recall that pressure is equal to force divided by area, and that pressure is equal to density times the gravitational constant times H, where H is the depth. Where H is the depth here. Because there should be more pressure as we go farther down. All right, so I'm going to start with this side right here, this face. I want to find the force that's being exerted on that face. So I'll take my equation here. I will solve it for force. And then I have the pressure in the area, and I can just multiply these things, right? Delta GH times 150. How does that sound? Can I do that? Can I take density times gravity times H times 15 times 10? Why not? Absolutely. So what is that changing? I mean, what does that mean that I'm at different heights? My pressure changes. My pressure is not constant in this area. My pressure times area equals force assumes that the pressure is constant throughout that area. It's not in this case. So I can't just use that formula. The pressure is changing throughout this area. So I have to cut a thin slice. I cut a thin slice in this direction because in that little tiny slice of area, my depth is constant, and therefore my pressure should be constant. So I really just want to find the force in this thin slice. And in this thin slice, because the pressure is constant, it should just be pressure times the area of that slice. And once again, we've taken this hard physical problem and turned it into an area problem. These are problems we've done before now. Now pressure really is density times G times H. So once again, if we're talking about water here, then the density of water is 62.4 pounds per cubic feet. We'll say all our distances are in feet. So in this case, I would have 62.4 times H times my delta A. Delta A in this case would have a width of 10 and a thickness of delta H. And that should be the force in this slice. Find the total force, what am I going to do? The integral of all this stuff. From 0 to 15. Any questions about this problem? All right, so that's that side. What about the bottom? How do we work on the bottom now? Take a second, see if you can work with your groups on your whiteboard. How are we going to find the force on the bottom of this tank? All right, I'm not going to give you too much time for this one because I want to talk about it. All right, we're setting up this problem. Should I cut my slices this way or should I cut my slices this way? Neither. Why do we cut slices? And because the value is not constant, but in this case, because we're working all at the same depth on the bottom, the pressure is constant everywhere on that bottom face. Everywhere along that bottom, the pressure is delta times G times 15 along that whole bottom. So because it's just a constant throughout that whole area, force is just pressure times area. Pressure really is 62.4 times 15 because that's the depth everywhere along that bottom. And my area is just 200. We don't need gravity because it's pounds per feet. We need gravity if it's kilograms or grams or some unit of mass. That's the difference between a mass density and a weight density. A weight density gives me the weight, which is a measure of force. Mass is the amount of a material. They're subtly different. They differ by a constant, which is why we sometimes think about weight in terms of mass, but if you were on the moon, your weight would be different, your mass would be the same. All right, a question about this problem. This is one of those trick questions, right? You can integrate, and if you integrate it right, you'll get the same answer, but you just don't need to. It emphasizes the point of why we're doing calculus. Now, we do it for hard problems. We do the easy problems the easy way. Okay? Questions? All right, so now we got some problems I believe are on the homework. This is a trough. It's a classic trough problem. It's full of water. Find the force of the water on the triangular end. So find the force on this face is at part A, and part B is find the work to pump all the water over the top. You know, we just did that one in the warm-up, though. So that's lame to repeat it. Let's look at a different problem. Let's do this one. Okay, I just wanted the integral set up for this one. We have a different style of trough here. It's a little harder to work with. We have a trapezoidal face instead of a triangular face. Assume that trapezoid on the front is very nice, that it's symmetric about its center, and it's a perfectly drawn trapezoid, which doesn't look to be. Okay? So assume that trapezoid is a very symmetric, beautiful trapezoid. And see if you can work through these four integrals. We'll give you a good 7-8 minutes. That should say weight of the oil, I guess. Weight of the oil. Two y. Our density is 2y. picture this thing full of water and there's oil in there. It doesn't mix properly, and so it's more on the surface-ish. So it's more dense with oil at the top. So here we should say y is the distance from the bottom. I'll do a sketch up there to help you get started on finding that piece. There are other ways to do this piece as well, but this is one way. Remember, I just did a setup. You don't actually have to evaluate them. All right, so we want to find the weight here. Let's start with the first one here, the weight. Well, if I want to find the weight, I should just be able to take the density times the volume, right? I want to get pounds. My density is pounds per cubic foot. Pounds times my volume should give me this value. Can I do it all at once, though? I can't do it all at once. It'd be nice because if I could just find the area that trapezoid and multiply by the length to find the volume, that would be really great. But in this case, my density is a function of y. Maybe this is oil sitting in water or something that's accumulating more at the top than the bottom. Whatever the physical situation is, our density is a function of the height. So we have to account for that. So we really do have to cut our slice and find just the weight in our slice. Okay. So let's see, I'll call this delta W for the weight in my slice. That's going to be my density times the volume of my slice. Now, how do I find the volume of my slice? Well, I have a length. The length is 15, so that's not too bad. And the thickness is going to be my delta Y, but it's really that width of that front face that's a tricky piece. And so this diagram is one way you can set this up. For this trapezoid, because it's all symmetric and nice, I can kind of think about it as two triangles and a rectangle in the middle. And so if I'm just looking to find this edge piece right here, then I'm back to my similar triangles case. Okay, from my diagram. So now I can just do the ratio over here. Apparently I have too many W's here. But if I wrote this ratio out, it would be the width is to 3 as the height is to 10. So W would be 3/10 times Y. And so this distance right here, that I'm still missing in my volume, is really two of these pieces plus 6. Right, it's this length and this length plus 6 in the middle. So this one should be 2 times this value, so 3/5 Y plus 6. That would be the width of one of those slices, the full width there. Questions about that? All right, so this is really the representation for my volume piece. And so I could just find my total weight now is just the integral of my density times that piece there, 3/5 Y plus 6 times 15 dy. And I could write in my density value. Now, center of mass is kind of weird for this question. We don't really have mass here, but mass is just a constant difference than pound, essentially. And so because it's a constant difference, it would just kind of factor out. So we can really use that same process, that same formula we were working with before. So really the center of mass, if I thought, well, where is that center of mass? If my density is only changing with respect to y, then the rest of my volume piece has a bunch of symmetries. So I could say, you know, if this is my x direction, for instance, I don't have to calculate the x center of mass because it's going to be in the middle, because my volume is symmetric in this direction, and the density doesn't vary in that direction. So it's going to be somewhere along this middle line. And I say, well, where is it in maybe this direction, the z direction? Well, once again, our density isn't changing that direction, and the shape is symmetric in that direction. So the middle is going to be the middle. So it's going to be somewhere along this line. So I know it's back here, back here. I really just don't know the height value at that center of mass. So I can really simplify everything by just looking for that one direction. So in that case, I'm going to just find the y center of mass as I've drawn it. It'll be the integral of y times my mass calculation, and then my total mass calculation in the denominator. Once again, the mass and the weight, they're just different by a constant, so that constant could just factor out of both integrals and cancel each other out, so it really kind of is a wash. And so I can look at this top one as y times the density times the volume, and the denominator would just be density times volume, but I just set up those integrals. Right, this is just the total weight, and this is just y times the total weight. So I would just factor another factor of y in here. Questions about that? All these integrals are going to look very similar, because really, you start from those first fundamentals of drawing your slices, and they're all going to end up with the same delta v, or maybe a delta a that's going to require the same length, but it's all really that same geometry here. The next one, the work required to empty the tank. Well, if I think about the work just to empty one slice, and unfortunately I'm using W again here, it's my third W, I think. It should just be the distance I'm going to move the slice and the weight of the slice. So if I'm going to take this slice and move it to the top, what's the distance I'm moving it? (10 minus y). That's the distance I have to move this. And now I need the weight of the slice. Well, I've already done the weight of the slice. It's just this piece. It's just delta times delta V. That's the answer to my first problem. So really, it's the same integral as part 1, except I'm slipping in this little 10 minus y piece. And then we look at the last one, the force on the front face. So if I just look at a little area along the face, this piece right here, I say along that thin strip of area on the front, my pressure is constant, so I would get the force on that face is just the pressure times the little slice of area in that face. Pressure is my density, which is 2y. I don't need g because it's a weight density. Times the depth. What's the depth here? Once again, 10 minus y. We have to be careful here. The depth is not the height of the slice. It's the distance down. And then I have my dA piece. I pretty much have dA. I have delta V, and the only difference between delta A and delta V is just that length factor. So if I just remove this factor of length, I get the area of the slice. So this one would be 3/5 y plus 6 delta y. All right, a lot of material there. Went through it pretty quick here. I'm really trying to stress how similar all these values are. So you really should work from first principles and set all these things up. All right, so next time it's going to be a work session. So we're going to have some problems. I'm going to email out a practice exam a little bit later today, probably in an hour or two. You can start and work on that. You have a little bit of time to work on that in class, and you'll go through some questions from it. And office hours are right now.